In this video, we're going to do a second example of the control volume analysis using conservation of momentum. And here we're an engineer and we're asked to find the thrust on a windmill in a 10 meter per second flow where we're given the diameter of the streamlines upstream and downstream. Okay? So this is a pretty relevant exercise for those of you interested in sustainable energy. What we really want to know is how much energy are we able to pull from the wind for a particular windmill. And in many cases, we would expand that to wind farms of hundreds, if not thousands, of individual windmills. But this is a very typical type problem that you're asked to solve in these types of engineering situations. Okay, so we're going to use our recipe. We're going to start with define control volume. So we're going to define the control volume. Okay, so in all our previous examples, we had a finite boundary that we could draw the control volume along to get rid of several of our surfaces. But here we don't have that, so things get a little more complicated, but luckily for us, not that much. And the reason for that is we're given streamlines. And if you recall, streamlines are lines where the velocity is everywhere parallel to the line. Meaning that if we draw our control volume such that it's perpendicular to this surface, then travels along the streamline, and then it's perpendicular to this surface, like so, and then along this streamline on the other end, we now have a control volume where the top and the bottom, because they're on the streamlines, by definition, the term V dot dA is going to be 0, therefore there's no flux across those boundaries. Even though we don't have a solid boundary, we can still get a control volume defined where there's no flux across some of the boundaries, simplifying our problem. So from there, we're going to label our two surfaces, surface 1 and surface 2. So we've now defined the control volume, and we have two surfaces we need to be concerned about. One is the upstream surface, and 2 is the downstream surface. Okay? So, second is apply conservation of mass. And we want to do that because we don't know the velocity downstream. We know the upstream velocity and we know the width of the streamline. So let's write it out in its full form. D over dt times the integral over the control volume, rho dv, plus the integral over the control surface of rho v dot dA is equal to 0. We're told that in the problem statement that the flow is steady. It's a steady 10 meter per second wind, so we can assume that the flow is steady. So this first term drops out, so that's 0. Okay. And then because of the way we've defined our control volume, the flow is perpendicular to both surface 1 and 2, so we can take that V dot dA and get is simply U times A. And so we can get the same expression we had in the previous example. We have negative rho U1 A1 is plus rho U2 A2 is equal to 0. We can rearrange and get U2 is equal to U1 A1 over A2. We can plug in our numbers there. We have 10 meters per second times, now we're not given the area directly here, we're given the diameter at 3 meters. So we can say pi over 4 times 3 meters squared. It's the area of our streamline or control surface over pi over 4 times 4.5 meters squared. Okay, and that gives us a velocity U2 equal to 4.44 meters per second. Okay, so now we have the downstream velocity. Step 3, apply conservation of momentum. Okay, again, we're going through our recipe. Control volume, conservation of mass, conservation of momentum. All right, so again, we only have forces in the x direction, so we're going to say the sum of the forces in the x direction is equal to d over dt integral over the control volume of rho u dv plus the integral over the control surface of rho u v dot dA. Okay? We're told again that the flow is steady in the problem statement, so this term goes to 0. And so we just have the sum of the forces in the x direction is the difference, is equal to the flux across the two boundaries, okay? So we can do that pretty straightforward. So if we look at the surface 1, we have negative rho u, and v dot dA is going to just simply be u times a. So we have the sum of the forces in the x direction is equal to negative rho u1 u1 a1 plus, and the same thing in the on control surface 2, we have rho u2 v dot dA is u2 times a2, and that's in the positive direction because it's an out. So rho u2 u2 a2. Okay, now we can plug those numbers in. We know the density of air, so we have negative 1.2 kilograms per meter cubed times 10 meters per second squared, because there's two u1s there, times pi over 4 times 3 meters squared. All right, plus 1.2 kilograms per meters cubed times 4.44 meters per second squared, because there's two of them, times pi over 4 times 4.5 meters squared. We could throw that into our calculator. We get the sum of the forces in the x direction is equal to negative 472 newtons. Okay, so now we have the force on the control volume. Now we need to go to statics and do our free body diagram. So now for determine forces. So if we draw our free body diagram, so say if that's the windmill, we have the force on the fluid, Rx. So we'll call this the reaction force, Rx. So that's the force on the fluid at the control volume. What else do we have? Well, the entire windmill's at gauge pressure, at atmospheric pressure, and so there are no real pressure forces across the two control surfaces. So the only force we have is Rx. So we end up with Rx is equal to negative 472 newtons. Now again, that's the force on the fluid. So the force that the windmill experiences, or the thrust that would be affecting the windmill, we employ Newton's third law, and we say it's equal and opposite. So that force on the windmill is going to be equal to 472 newtons. And that's our answer for this problem. Okay? So the key point here is that if we pick our control volume correctly, we can really simplify the problem. If we had gone across those streamlines, then the integrals get hairy and you're going down a world of hurt as far as solving the problem. But if we pick the control volume, because it's ours to pick, we can pick it so that the problem becomes much easier to solve. Okay?